Imagine you step into cold water just for 30 seconds. Maybe it is a cold shower, maybe it is a lake, maybe it is a pool first thing in the morning. 30 seconds. That is it. And in those 30 seconds, something happens inside your body that most people have never been told about. Something that goes all the way down to the atomic level, to the individual molecules inside your cells, to the proteins folded in your blood, to the neurons firing inside your brain. Not figuratively, literally, your atoms rearrange, your chemistry shifts, your nervous system rewires its priorities in real time. And the question is not whether any of this is happening. The science is not in dispute. The question is whether you understand what is actually going on inside you when you do it. Because once you see the mechanism, cold water is never the same again. If you have ever wondered why cold water feels like it punches you in the chest, and then somehow makes you feel better than almost anything else, stay with this until the end, because the explanation is going to change how you think about your own body. And if you find this kind of deep science genuinely useful, consider subscribing, because this is exactly the kind of content we build here every week. The first thing you need to understand is what cold actually is, not as a sensation, but as a physical event. Cold is the absence of heat. Heat at the molecular level is motion. When atoms in a substance are moving fast, vibrating rapidly, transferring kinetic energy to neighboring atoms, that substance is warm. When they slow down, it is cold. So when you step into cold water, what is physically happening is that water molecules moving at a relatively slow speed are coming into contact with your skin, which is warm, and they are pulling kinetic energy away from your surface tissue. Your atoms are donating their movement to the water. Your skin temperature dropped by several degrees Celsius within the first few seconds. That thermal gradient, the difference in temperature between your body and the water, is the engine driving everything that follows. Now here is where it gets interesting. Your body has one absolute biological priority above all others, and that priority is thermoregulation, keeping your core temperature within a narrow band of roughly 36.5 to 37.5 degrees Celsius. Everything your body does in cold water is organized around that one goal. Every hormonal shift, every neurological response, every cardiovascular adjustment, it is all in service of that single imperative. Understanding that gives you a framework for understanding every single thing that happens in those 30 seconds. The first response, and it happens within milliseconds, is the activation of a specific class of nerve endings called cold thermoreceptors. These are concentrated heavily in the skin, particularly in areas like the face, the chest, and the hands. These receptors detect the rapid drop in temperature and send an immediate signal up the spinal cord to the brain, specifically to the hypothalamus, which is the thermoregulatory command center of the body. The signal is not subtle. The hypothalamus receives what is essentially an emergency alert: surface temperature dropping, core temperature at risk, respond immediately. And the hypothalamus does respond immediately with a cascade of physiological changes that is one of the most coordinated and dramatic responses in human biology. The cardiovascular system is the first to show a visible reaction, and you have almost certainly felt it, even if you did not know what it was. Within the first 2 to 5 seconds of cold water exposure, your heart rate does something counterintuitive. It drops. Not permanently, not dramatically, but measurably. This is called the diving reflex, or the mammalian dive response, and it is one of the most ancient survival mechanisms in vertebrate biology. It is the same reflex that allows marine mammals like seals and dolphins to slow their heart rate dramatically during dives in cold water, conserving oxygen and protecting vital organs. In humans, it is less extreme, but it is real, and it is measurable. Studies using cold facial immersion have recorded reductions in heart rate of anywhere from 10 to 25% within the first few seconds of exposure. At the same time that the diving reflex is slowing the heart, a second and opposing response is also beginning. Your sympathetic nervous system, the branch of the autonomic nervous system responsible for the fight or flight response, is starting to activate. It is releasing norepinephrine, also called noradrenaline, into the bloodstream and directly into tissues across the body. Norepinephrine is causing peripheral vasoconstriction, which means the blood vessels near the surface of your skin and in your extremities, your hands, your feet, your arms, your legs, are narrowing. They are physically constricting, reducing blood flow to the periphery. The blood is being redirected toward the core, toward the heart, the lungs, the kidneys, the brain, the organs that need to stay warm to keep you alive. Your body is performing triage in real time, deciding which tissues get priority access to warm blood and which ones can tolerate a reduction. This is where the cold water experience starts to feel paradoxical to most people. You step in and you feel an immediate shock, a gasping response, a sudden urge to breathe rapidly, and then, if you stay, something strange happens. The initial panic begins to settle. Your breathing slows. A kind of clarity begins to emerge. That is not psychological willpower. That is neurochemistry. What is happening is that the competing signals, the parasympathetic diving reflex slowing the heart and the sympathetic activation raising alertness, are producing a state that has no real equivalent in everyday life. Your heart is being held at a lower rate while your brain is being flooded with norepinephrine. The result is a kind of calm alertness, a focused stillness that is neurologically distinct from anything you experience at room temperature. The norepinephrine release deserves its own attention because the numbers involved are genuinely remarkable. Research by Dr. Rhonda Patrick and others reviewing the cold exposure literature has cited studies showing that cold water immersion at temperatures around 14 degrees Celsius can increase norepinephrine levels by 200 to 300%. Let that land for a moment. A 200 to 300% increase in one of the primary neurochemicals of focus, alertness, and mood elevation from 30 seconds of standing in cold water. Norepinephrine plays a central role in attention, in working memory, in motivation, and in the regulation of mood. It is also a key target of several classes of antidepressant medications. Your body is producing a massive spike of it simply by detecting cold at the skin surface. But the story does not stop with norepinephrine. Cold water exposure also triggers the release of dopamine, though the mechanism is indirect. Dopamine is released in anticipation of reward and during the relief of discomfort. The moment you step out of cold water, or even during the process of enduring it, your brain begins releasing dopamine in patterns researchers have described as sustained rather than spiked. Unlike the sharp dopamine hit of, say, social media or sugar, which rises fast and crashes, the dopamine associated with cold exposure appears to remain elevated for a longer period after the exposure ends. Studies have documented mood elevation lasting for several hours following cold water immersion, and this sustained dopamine pattern is one of the leading hypotheses for why. Now let us go deeper, because there is something happening at a truly microscopic level that most people never hear about, and it is one of the most fascinating aspects of cold exposure biology. It involves a protein called norepinephrine, again, but this time in its role not as a neurotransmitter but as a signal molecule, triggering a process called cold shock protein activation. When your cells are exposed to rapid temperature drops, they begin producing a family of proteins called cold shock proteins. These are molecular chaperones, proteins whose job is to help other proteins maintain their correct three-dimensional shape under stress. Because here is the thing about proteins in your body, they are not just passive building blocks. They are folded structures, and that folding is everything. A misfolded protein does not work. It can become toxic. Your cells are continuously monitoring protein integrity, and temperature stress is one of the most serious threats to that integrity. Cold shock proteins, particularly a protein called RNA-binding motif protein 3, or RBM3, have been studied extensively in the context of cold exposure. Research, including work published in journals like Nature, has shown that RBM3 plays a role in synaptic regeneration, literally the rebuilding and strengthening of connections between neurons. In animal studies, cold exposure that triggered RBM3 production was associated with protection against synapse loss in models of neurodegenerative disease. The human implications are still being studied, but the mechanism is real and the data is compelling. Your brain, under the stress of cold, may be triggering a cellular maintenance response at the molecular level. There is also what is happening to your mitochondria. Mitochondria are the energy-producing organelles inside your cells, and they are extraordinarily sensitive to temperature. When your body detects cold, it begins a process called thermogenesis, the generation of heat. There are two types: shivering thermogenesis, which is the muscular contractions that generate heat through friction, and non-shivering thermogenesis, which occurs primarily in a specialized tissue called brown adipose tissue, or brown fat. Brown fat is metabolically remarkable. Unlike regular white fat, which stores energy, brown fat burns energy to produce heat. It does this using a protein called uncoupling protein 1, or UCP1, which allows mitochondria to generate heat instead of ATP. In adults, brown fat deposits are found primarily in the neck, the upper back, and around the kidneys. Cold exposure activates these deposits, and consistent cold exposure over time actually increases the amount of brown fat tissue you carry, increasing your long-term capacity for thermogenesis. This is where the metabolism story begins to get significant, because brown fat activation is metabolically costly. Studies have measured that cold exposure sufficient to activate brown adipose tissue can increase whole-body energy expenditure by measurable amounts, with some research documenting increases of 80% or more during acute cold exposure. Now, 30 seconds in a cold shower is not going to transform your metabolism in isolation. But as a recurring practice over weeks and months, the cumulative activation of brown fat and the adaptations it drives, including mitochondrial biogenesis, the creation of new mitochondria inside cells, is a real and documented biological effect.
This is a good place to pause.
Because if you are finding this useful, and you want to understand more about how your own biology responds to everyday choices, subscribe right now and turn on notifications. The science of human performance and how the body actually works is what this channel is built around, and there is a lot more where this came from. Let us talk about the immune system, because this is one of the most contested and most misunderstood areas of cold exposure research. You have probably heard two completely contradictory things. Cold water is good for your immune system. Cold water suppresses your immune system. Both statements exist in the literature, and both require context to be meaningful. Here is what the research actually shows. Cold exposure triggers an initial release of cortisol, the same stress hormone that is central to the body's acute stress response. Cortisol in the short term has an immunosuppressive effect, reducing inflammation. But the cold also triggers the release of norepinephrine, which, in addition to its neurological effects, has direct effects on immune cell activity. Specifically, norepinephrine and cold exposure have been shown to increase the production of cytokines, particularly interleukin-6, which plays a complex role in both pro-inflammatory and anti-inflammatory signaling depending on context. The famous Wim Hof study published in PNS in 2014 is the most cited piece of evidence in this area. Researchers at Radboud University in the Netherlands trained a group of volunteers in cold exposure techniques and then injected them with bacterial endotoxin to induce an immune response. The cold-trained group showed measurably reduced inflammatory symptoms compared to controls and showed higher levels of anti-inflammatory cytokines. The researchers were careful to note that the cold exposure was combined with specific breathing techniques and that separating the effects of the two was methodologically difficult. But the immune signal was real and statistically significant. What is also real is that chronic cold exposure performed consistently over weeks appears to increase what researchers call adaptive thermogenesis and also appears to upregulate certain immune functions, including natural killer cell activity. Natural killer cells are a class of immune cell that identifies and destroys infected cells and tumor cells before the adaptive immune system fully engages. Elevated natural killer cell counts and activity levels have been documented in populations with regular cold water swimming habits. The mechanism is not fully characterized, but the pattern is consistent enough to be taken seriously. Now let us return to the nervous system, because there is one more layer of what is happening in those 30 seconds that most people never reach, and it is arguably the most important for long-term mental health. Your autonomic nervous system has two main branches: the sympathetic, which activates the fight or flight response, and the parasympathetic, which governs rest and recovery. In everyday modern life, most people's autonomic nervous systems are stuck in a low-grade sympathetic state. The chronic stress of work, screens, noise, and decision fatigue keeps the sympathetic branch slightly elevated almost continuously. This is not catastrophic in the short term, but over years it erodes things: sleep quality, immune function, cardiovascular health, emotional resilience. Cold water exposure is one of the very few stimuli that forcibly engages both branches of the autonomic nervous system simultaneously and at high intensity. The cold thermoreceptors activate the sympathetic system. The diving reflex activates the parasympathetic system. Your body has to navigate the tension between both in real time, and what researchers have observed is that people who practice cold exposure regularly show improved autonomic flexibility, meaning their nervous system becomes more responsive and more quickly recoverable. It gets better at switching between states, better at activating when needed and recovering when not. This is sometimes called vagal tone, reflecting the health of the vagus nerve, the primary parasympathetic nerve running from the brainstem to the gut. Higher vagal tone is associated with better emotional regulation, better stress recovery, and better cardiovascular health. There is also the psychological dimension, and here the science is still developing, but the patterns are striking. Cold water exposure requires and trains what researchers call interoceptive accuracy, the ability to accurately perceive and interpret signals from inside your own body. When you step into cold water, you are confronted with a very strong internal signal, the shock, the urge to gasp, the discomfort, and you have a choice about how to respond to it. You can catastrophize it, you can surrender to it, or you can observe it accurately, understand what it is, and regulate around it. People who practice cold exposure regularly report improvements in their ability to do this not just in cold water, but in other stressful contexts. The cold becomes a laboratory for nervous system training. Research by neuroscientists, including those studying the interoceptive network, have documented that the anterior insular cortex, the region of the brain most associated with interpreting internal body signals, shows increased activity during cold exposure, and that this activity is correlated with individual differences in how people manage discomfort and emotional distress. Training the insular cortex through repeated cold exposure may, in other words, be training the very neural infrastructure that underlies emotional regulation. One more piece of the biology deserves your attention before we bring this all together, and it is the endorphin system. Endorphins are endogenous opioid peptides, meaning they are opioid-like molecules produced inside your own body. They bind to the same receptors as opioid drugs and produce analgesia, meaning pain relief, and in high concentrations, euphoria. Cold exposure stimulates endorphin release, and this is one of the reasons the post-cold water feeling is so distinct and pleasurable. It is also why regular cold water swimmers often describe a mild but real sense of addiction to the practice. The endorphin hit is real. The chemistry is not metaphorical. You are producing pain-relieving, mood-elevating molecules inside your own cells because you chose to stand in cold water for half a minute. What is remarkable about all of this, and it is worth sitting with, is how many completely different biological systems are activated by a single, simple 30-second exposure to cold water. Your cardiovascular system is doing triage. Your nervous system is running two opposing programs simultaneously. Your cells are producing cold shock proteins to protect molecular integrity. Your brown fat deposits are burning energy to generate heat. Your immune system is recalibrating its inflammatory signaling. Your brain is releasing norepinephrine, dopamine, and endorphins. Your vagal tone is being trained. Your insular cortex is being exercised. All of that from 30 seconds of choosing not to turn the hot water on. The human body is not fragile. It is not a machine that needs to be protected from discomfort. It is a system that was built by millions of years of evolution to respond to exactly this kind of stress, to take a challenge and use it as a signal to adapt, to upregulate, to become more capable. The problem is that modern life has removed most of those signals. We live in thermally neutral environments, in temperature-controlled buildings, in carefully managed comfort, and the absence of thermal stress is, biologically speaking, an absence of one of the primary triggers for adaptation. Cold water is a way of reintroducing that signal deliberately, of telling your body that the environment is not completely predictable, that it needs to stay ready. Now, none of this means that cold water is a cure for anything. It is not a substitute for sleep, for nutrition, for exercise, for genuine mental health care. If you are dealing with serious physical or psychological health challenges, a cold shower is not the intervention, but as an adjunct to a life designed around health, as a daily practice that costs nothing and takes 30 seconds and activates more biological systems than almost anything else you can do in that amount of time, the case for it is strong, and crucially, the case is built on mechanism, not on trend. It is not popular because influencers do it in ice baths and post the video. It is popular because when you understand what it is doing to your atoms, to your proteins, to your neurons, the choice to do it becomes almost obvious. Before you close this out, here is what is worth doing. Tomorrow morning, when you get in the shower, finish the last 30 seconds in cold water. Do not think about whether you want to. Just do it and pay attention to what happens inside you. Notice the breathing shift. Notice the moment the initial shock settles. Notice how you feel in the 20 minutes after. You will have a much more direct relationship with everything this script described, because you will have felt it. And if you want to go deeper into the science of how your own body works, how your brain, your gut, your hormones, and your nervous system respond to the choices you make every day, that is exactly what this channel is for. Subscribe, share this with someone who would find it useful, and we will see you in the next one.